Welcome to Safety Engineering Briefings. Short, practical insights for software and security engineers. Last year, a major airline grounded flights for several hours, not due to weather or mechanical failure. A misconfiguration in their new passenger manifest system allowed unauthorized access to crew scheduling. Simple mistake. Huge impact. We build systems to be secure. Yet, these failures happen. It's not about lacking security controls. It's about how those controls behave when everything else is moving. We often think of security as a checklist. Do we have encryption, authentication, authorization? Check, check, check. But security isn't a property of code. It's a property of a system in operation. That's a crucial difference. A system is code, infrastructure, people, and processes, all interacting. A perfectly secure component can be rendered useless by a flawed process, or a misconfigured server, or a tired operator. A common misconception is believing security is a solve-once problem. You build it, you test it, you deploy it. Done. That's not how reality works. Systems change. Dependencies update. New threats emerge. What was secure yesterday might not be secure today. We need continuous verification, not just initial validation. Another issue is focusing too much on preventing attacks, and not enough on limiting their blast radius. Assume breaches will happen. It's not pessimism. It's realism. Design your systems to minimize the damage when they do. Compartmentalization is key. Limit access. Segment networks. Use least privilege. Finally, we often underestimate the impact of operational complexity. The more moving parts, the more opportunities for something to go wrong. Simple systems are easier to secure. Complex systems require exponentially more effort to maintain security. Engineers often add complexity believing it provides more features or scalability. But that complexity introduces risk. Always ask, is this complexity truly necessary? Consider a typical e-commerce platform. They use a microservices architecture. Order service, payment service, inventory service, all communicating via APIs. They've implemented strong authentication and authorization for each service. Great. But what happens when the inventory service experiences a surge in traffic during a flash sale? The autoscaler spins up new instances. But a recent code change introduced a bug in the instance configuration. New instances don't have the latest security patches. An attacker exploits this vulnerability, gaining access to the inventory database. They can't directly access customer payment information because of the service boundaries, but they can manipulate inventory levels, causing significant financial loss and reputational damage. The initial security controls were in place. The system still failed. The failure wasn't a flaw in the authentication code. It was a failure in the deployment pipeline and the incident response process to detect and remediate the misconfigured instances. Secure systems fail in production not because of missing controls, but because of systemic weaknesses in operation. Focus on continuous verification, limiting blast radius, and managing operational complexity. Ask yourself, what assumptions are we making about the environment our system operates in, and how can those assumptions be invalidated? If this topic was useful, take a moment to reflect on how it applies to your own systems. See you in the next briefing.